increasingly, neural methods are being used to study human language understanding so that we can get beyond just the behavior and understand the computational and hopefully ultimately the implementational physiological basis for how language processing and representation of knowledge work. There are different kinds of methods that are available. Obviously, we cannot use all the methods that we would use on a non-human species on a human. And so we have various trade-offs between the temporal and spatial method resolution of different methods, which populations they can possibly be used in, and what we can hope to get out of them. In these kinds of experiments, a lot of the time, people are going to be a little more passive than in the behavioral studies that I've just talked about. They might simply sit back and listen to or read a sentence word by word. And the question of, for example, what is difficult and what takes time, which was brought forward very clearly, say, in the study of reading, as we described earlier today, is going to become a little less straightforward. But nonetheless, there are general and striking results that we can find and interpret. So, for example, one of the widely used methods and one of the earliest methods for the study of the neural basis of language was electrophysiology, EEG. And in this case, we simply hook up a cap with electrodes to the head of the patient, of the participant, and have them, for example, read a sentence. So in the rapid serial visual presentation method, people are asked to just look at the center of the screen. So go ahead and look at the center of the screen, and I'm going to flash a bunch of words at you in fairly rapid succession, forming a sentence. Okay, so you might have found yourself a little bit jarred at the very end, and in fact, that's actually quite strikingly measurable from your scalp in terms of the electrical signal that's being generated by your brain. It's an amazing thing, but this is now a 40-year-old highly, highly robust result. That kind of surprise effect that you experienced at the word sock evokes what's called an N400 effect in language comprehension. What is an N400 effect? First of all, let me give you 3 different versions of a sentence to see the minimal set that is being compared. So in the context, he took a sip from the, we would be comparing drink, which is a normal continuation, waterfall, which is somewhat incongruous. It's possible, but it's sort of a weird thing to imagine. And then something that's extremely hard to imagine, maybe not impossible, but extremely hard to imagine, transmitter. And so we have these 3 different versions. And just to orient you to how this is looked at here, for historical reasons, these are plotted on a chart where the x-axis is time from the onset of the word, when the word would drink, waterfall, or transmitter was flashed, and the y-axis is microvolts, but it's done in a way that negative is up and positive is down for historical reasons once again. And figures B and C from the original Kudus and Hilliard paper on this is now a classic, looked at the relationship between the solid line was the normal condition, averaged over many subjects and trials, with many different items for these kinds of cases where, once again, we always had a normal, moderate, and strong. And this is the contrast between the normal and in solid and the moderate in the dashed line. And you can see that these larger ticks are 300 milliseconds. So about 400 milliseconds, there's this maximal deflection difference between the normal and moderate conditions, and that's a moderately sized N400. In contrast, in the strong condition, you get at a relatively similar time, drink versus transmitter, you get a larger deflection. And so there's a larger size effect. And this happens at a number of different electrodes. These refer to different electrodes on the head, and it's a fairly robust, widely distributed effect. And so it's not just at a single electrode that it's picked up. So that's the N400 effect. And this is generally fairly well understood to be something relating to the semantics and or expectation, but the fine details are not fully understood. And what exactly this effect is and isn't is still a matter of debate in the community. So that's one component in the ERP. So ERP is the evoked reaction potential or evoked response potential from language comprehension, which is a result of analyzing the EEG signal in a certain way. Here's another component, what's called the P600. And to understand this, let's look at what I'll call mismatches to lexically specified semantic properties. So the man prepared herself for the interview. This you're going to find jarring as well, the word herself. And this evokes a contrast. If I compare it, the definition, what we'll call this lexically specified or definitional mismatch effect. This is the response profile at a central electrode right about the top of the head to the man herself version at the word herself. And we can contrast that with the definitional match case where the same sentence was used except herself became himself, so there was no anomaly. Here you can see relative to the no anomaly case, the deflection is downward in the positive direction, and so it's P for positive, and it seems to max out starting around 600 milliseconds, although it lasts longer than the N400 effect does. Interestingly, this happens not only with these kinds of lexically specified cases, but to stereotypical semantic properties as well. So for example, the nurse prepared himself for the operation. It's well known, we all know that nurses can be can be male, but nevertheless, this word himself induces a stereotype mismatch effect relative to the stereotype match effect. In fact, actually, you can also see these stereotype mismatch effects for gender expectations in reading. So they're actually, unfortunately, as a commentary on our social situation, a very prevalent kind of effect in real-time incremental language processing. So that's EEG. fMRI is also used to study the brain basis of language. And MRI is measuring something that can be used so MRI itself as a measurement technique can pick up changes in blood flow associated in the brain, activation associated with blood flow. And F is for functional, that's looking at the changes in the blood flow rather than looking at the structural static properties of the brain. This is slow because it takes a matter of seconds for the blood in the brain to flow differentially to the parts of the brain that are most active. That's what's going on when a part of the brain is very active. It attracts more blood. And that's going to lead to a differential signal that's picked up by MRI. But there's very good spatial resolution for which parts of the brain are active in processing. So if you can get a participant to hold their head still, which they have apparatus to do, then you can actually get very fine-grained localization of where in the brain is more active versus less active, as evidenced by blood flow dynamics. So for example, a by now classic study by Fedorenko et al. 2011 contrasted sentences like a rusty lock was found in the drawer to sequences of non-words, for example, daptrello, smob, plid, cav, krev, replode. And this was done with a word-by-word RSVP paradigm, as we saw before, and then there was a test to keep people on target. They would answer with a button press as to whether which of the words, whether a word was in the context in the sentence or non-word sequence that they saw. For example, they might present lock, in which case the participant should press the yes button, or pair, in which case the participant should press the no button. And this keeps participants alert enough that the actual processing of the sentences by the brain, purely passively, elicits reliable and interpretable effects. We can contrast that with another experiment which involved verbal working memory. In particular, people had to see sequences of digit pairs and then match them to a numeric digit representation of the digit pairs and ask whether there was a match or not. So these are the tasks. So we have sentences, non-words, and verbal working memory. And this kind of method has actually turned out to help us gain traction on a perennial problem, which is, are there language-specific, language-dedicated regions of the brain? And this actually had been a controversial topic because there are sort of these famous Broca's and Wernicke's areas that for hundreds of years have been thought of as being encoding very specific language information in the brain, or potentially so. But that had become controversial over a period of decades during the 20th century. And what this study was able to show is that there are different parts of the brain that are very close to each other in space, but are functionally very distinct. In particular, in this area in the left inferior frontal gyrus that's illustrated here, there are areas that are sensitive in ways to not only the sentence non-word difference, so sentences evoke more response in these regions than non-word sequences, but also to the difficulty of a verbal working memory task. When the verbal working memory task is hard, it seems to evoke more activity in those parts of the brain, just in the same way as sentences do as well. And those seem, though, because these are not dedicated effects that are only about language, it seems to be arguable that perhaps those particular areas are ones that are not language specific. But there are other areas which are language selective. And in particular, The language selective areas are responsive to sentences, but not to non-words or any working memory task, regardless of its difficulty. So that kind of functional brain specificity can be revealed for language with fMRI techniques that don't need super fine-grained temporal detail. Now, there's also electrocorticography, which is sort of like EEG, but it's from the brain, not from the skull. There's a lot that is intervening between the skull and the brain. There's tissue, bone, and that weakens the electrical signal dramatically. So scalp measurements are, from a measurement quality perspective, not ideal. But of course, they're easy. Ordinarily, you don't have access to the brain of a patient directly. However, there are special conditions in which neurosurgeons need to access somebody's brain directly and leave the brain accessed for a period of time. In particular, pre-surgical epilepsy patients often go through a period where they get electrode arrays that are directly implanted on the surface of the cortex. These electrode arrays are then recording constantly, and they're monitored during a waiting period, where effectively the surgeon is waiting for some signs of an epilepsy episode to emerge, to figure out where in the brain it's coming from to help guide the surgery that will then ensue. And during the pre-surgical monitoring, many patients will generously donate their energy and time and attention to participate in all sorts of cognitive science, psycholinguistics, neuroscience experiments. And one of the really remarkable successful studies in the area of language using these electrocorticography results found evidence for what we might call neural phonemic representations. So these are different electrodes on the array, each column, and in the rows are the different phonemes of the English language. And what you can see is that there is a remarkable grouping structure for some of these different arrays. This is Mascarini et al. 2014, that show that, for example, all of these sounds were picked up very strongly by this particular electrode. This other electrode was selective for another set of sounds here. This electrode for another set of sounds, and so forth. And if you look closely, you'll see that actually these have some internal structure. These are the stops right here. The stop consonants, d, b, g, p, k, t, that we studied when we looked at voice onset time. These are fricatives. These are one set of fricatives. These are certain vowels. These are other vowels. And they actually have interesting substructure. And if you take a lot of electrodes and you actually do bottom-up clustering, what emerge from that are what look very close to be what a phonologist, a linguistics phonologist, would come up with as a representation of the featural decomposition, the featural representation of all the sounds of the language. This is quite a remarkable study. All of these things, these methods, give us scientific opportunities to develop comprehensive theory to account for the patterns of human language use and representation, but also engineering opportunities to help use human language processing, data from human language processing, to hopefully help guide the way to more human-like AI language using agents, and furthermore, AI agents that will understand why we use language the way we do.